of priority, then this is what these bits are used for. And so today, finally, where these bits are a bit the laughing stock of the protocol designers because they have changed continually. But as of now, and for quite a few years now, they've been stable at this definition, which is you have 6 bits that we call DSCP, which is basically priority bits. These are used to indicate priority. And then you have 2 bits that are used by a router to indicate to end hosts whether they've experienced congestion. So we call those ECN. Don't worry about ECN for now. We'll cover ECN when we get to congestion control. Okay, so remember the primarily indications of priority. And then the last bit is this idea of options. So here the thought was, what if my router needs to do more than just forward a packet? And so there were examples of things people thought that would be useful to do. One is, for example, this idea of recorder route. What if you want to trace the path a packet has taken? I want to be able to tell a router you need to record your ID or record the path as this packet is traveling. Or if you wanted timestamps for diagnostics or debugging reasons, you want the router to put a timestamp so you know at what time this packet arrived at this router. Third option that was common was this idea of source routing. What if I want to tell the routers, here's exactly the path I want you to follow, overriding what your routing algorithms told you. So the thought was you might have these more complex features or more advanced features, and the host should be able to tell routers what those features are. So this is why people designed IP options, again, not very widely used. Part of the issue with IP options, one was the minute you said, I have a whole set of optional fields, your header length is no longer fixed. Right? Your header length varies. And as you try to build hardware routers that process packets at very high speed, having to deal with variable length headers is complicated because the first thing you have to do is parse exactly what all these bytes are. So it's harder to have a parallel implementation, which is what allows hardware to go fast. And the second problem is many of these options, processing options, is an additional processing overhead on the router. And so they became ways of attacking a router. That if you want to attack a router, you send packets with lots of options set, and now you're exhausting resources at the router. So again, options kind of mixed luck in terms of how they get used on the internet. So, but 2 fields that you will see in your IPv4 header for that reason are these type of service bits and option bits. I'm going to very quickly just flash the IP header here at you because we've covered it. So we show the IP header, it's aligned on 32-bit boundaries, so 4 bytes. Fields you'd expect to see in the IP header for parsing, you have a version number, you have a header length, and a total length in bytes. The header length is counted in multiples of 32 bits, so in multiples of 4 bytes. We have the destination IP address, we have the protocol field, which tells us whether it's TCP or UDP or something else. We have the source IP address. We have the TTL and the checksum, it's 16 bits. And then we have a bunch of fragmentation bits that you'll design in section. And lastly, we have the type of service and some options. Okay, so if you go pick any IPv4 packet off of the internet and you look at it, this is what you'd expect. This is what you have to see. This is the protocol standard. Any questions? Okay, so just next time, which is not Thursday, but the lecture after that, we'll wrap up IPv4 to IPv6, what were the main changes in what we discussed, and then just a few security implications of the IPv4 header. Okay. With that, thank you.